Okay, let's drum up some fun with Bessel functions. And so we will look at a specific example. This is an example of drum vibrations, if you like, vibrations of a circular membrane. And many of the things we will do show up in problems that come from other contexts, problems having to do with vibrations, problems having to do with heat transfer, problems having to do with mass transfer in circular geometries, in viscous flow, in heat conduction, and in problems having to do with modern physics, vibrations of electrons or quantum mechanics, more precisely. Of course, problems of vibration arise in mechanics as well. So let's think about a circular membrane here, and any point on the circular membrane is going to be denoted by its displacement from the center, which is measured by this coordinate r, and orientation from some axis in terms of angular position, and that is denoted by theta. And so what we're going to assume is that this membrane, which makes up the head of this drum, is displaced out of its plane. So we tap on it, or we cause it to be displaced by some activity. We are drumming it. And so that displacement, out of plane displacement, is denoted by this dependent variable u, which is going to tell us how the drum vibrates. That is what we're trying to predict. That is the dependent variable. And it's going to depend on the position on the drum. So r and theta denote the position on the drum, and it's going to oscillate in time, it's going to vibrate, so it depends on time also, t. All right? The specification of the problem is that at the outer edge of the drum is of a known size, r equals a, that is the radius of the drum. The outer boundary of the drum is fixed, typically the rim of the drum. That's where the drum is kept taut, is kept fixed. And so that's the outer boundary. And so the displacement at this outer boundary at radial position r at any angular position theta at any time t is exactly equal to 0. It does not budge at all on the outer boundary. All right? And one more physical thing we can say is that the drum vibrates, and so the displacement is a finite displacement everywhere in the drum. It doesn't break. We're not sort of hammering it so hard that the drum just ruptures. All right? That situation is to be excluded. So we start by formulating a mathematical model. This mathematical model is essentially the equations of motion for the drum. And what it is that we apply Newton's law to a small element. We isolate a little element at position r and theta, and we apply Newton's law. We say that the acceleration of that little piece of material which makes up that drum is due to the net forces that act on the drum. And so we're not going to describe the detail of this mechanics here, but once you formulate this, it is relatively straightforward to show that one comes up with a partial differential equation, because this dependent variable u depends on r, theta, and t. It depends on three independent variables. So we have this partial differential equation expressing that variation. D square u dt square, that partial derivative in time, two partial derivatives in time, equals c square times del square of u, the Laplacian operator, which depends on r and theta. This coefficient here, c square, depends on the material properties that we have. C square is equal to the tension in the membrane, capital T, divided by rho, where rho is the membrane density. So if we have a heavy membrane made of some heavy material, then we will be, for the same tension, we will have a lower c. C has the interpretation of a wave speed. It's the speed at which disturbances can travel in this membrane. We can sort of work out the units here. T is tension, membrane tension, measured in units of newtons per meter. Membrane density is measured in units of kilograms per meter square. It's the membrane density per unit area of the membrane. And so if we take this ratio, newtons per meter divided by kilogram per meter square, recognize that Newton is nothing else but kilograms times meters per second square, mass times acceleration equals force, divided by meter here. And so if we clean this up, we'll see that the units are meters per second whole thing squared. So c has units of meters per second, or c has units of speed. Wave speed is how you can remember it. It depends in this way on the properties of the problem. All right? Okay, so here we have this PDE with a known c, and we have boundary conditions that we have described. And so what we want to illustrate is how, in a simple way, we can reduce this partial differential equation to an ODE, and then we will apply our methods to solve that ODE. And so let's consider the simpler case here. Let's consider the case where we have vibrations of this drum head that are cylindrically symmetric. All right, so this would be the situation where we tap on the drum right in the middle, or we tap it in a symmetric way. All right, and so in the cylindrically symmetric case, the displacement does not depend on the angular position, and so we drop the dependence on angular position, and we say that the displacement only depends on the radial location, and it depends on time. So it depends on two variables. All right, so to make progress, we are going to make a certain assumption about the form of the solution. And so we're going to say that the dependent variable, which depends on r and t, depends in this way, where the dependence on radius is given by a function capital R, which depends only on little r, the radial location, times a time function, which is given by this capital T, which depends only on time. So this idea, or this proposition, or this ansatz, that a variable, this dependent variable, depends in this way separately on space and separately on time, is the idea of separation of variables. This is a very general idea and can be exploited in many contexts. So we apply this idea, this ansatz, we substitute that in the partial differential equation. And so you can see that on the partial differential equation, on the left-hand side, we had the second partial time derivative in time, and so that will simply apply just to the time function. The radial function remains the same. And on the right-hand side, the del square operator in radius, when we have no azimuthal or angular dependence, is simply given by this expression here. This is the del square operator in cylindrical coordinates when there is no angular dependence, and time dependence is simply carried here. And so we have this equation, and so what we want to do is we divide this equation by capital R times capital T on both sides, and you can see that, and by c square, which is a constant. And so from here we can get to that by dividing this equation by c squared times capital R times T. So we would have this left-hand side, and this, when we divide it by capital R times capital T times c squared, this will go away, this will go away, and this thing will get divided by big R. And so this equation implies this equation, and then we can observe that the left-hand side of this equation involves things that depend on little t, on time, and only on time, whereas the right-hand side of this equation involves things that depend on little r, the radius, only. So there's no time showing up here, and there's no radius showing up there. And the equation says that these two must be equal. So the only way something which depends only on t can be equal to something which depends only on r is that both of these things are nothing else but a constant, because if they were to vary either in t or in r, they could never be equal to something else which depends on something else. All right? And so this must be a constant. And so now we have a choice of what is the value of this constant. And so this requires a little bit of thought, but let's think about this. Suppose we put the value of this to a negative constant. So with a minus sign times lambda square, so this is a positive number, times minus 1, so this is a negative constant. So if we put a negative constant and we look at the equation for time here, capital T function, you would see that the solution to that second order ODE is going to be sines and cosine functions, which are oscillatory functions in time. And this is what we expect, that if we disturb, the drum is going to vibrate, it's going to oscillate in time. And so we would like to have this dependence in time. If we make the other choice, if we put a positive constant here, then the sign of this term in the equation will change, and then we will get exponential solutions, exponentially growing and exponentially decaying solution, and that is not suitable for this drum vibration problem. So we can choose this on physical grounds, and so we have the time dependence given by this. And so once we have this choice, let's see what the radial dependence tells us. So Now with this negative constant here, this is the equation for big R. And so we're just rewriting the left-hand side. We're just expanding this derivative. When we take the derivative of R, we get simply 1. This is carried here. And then keeping R constant, we differentiate this, so we get that. And so that's the left-hand side. And so we can substitute that in the equation. We can clean it up. And the equation is presented in this way. And if we just do a further rewrite, we have in the equation this coefficient lambda times R showing up. And so if we redefine a new variable x, which is lambda times R, then this equation is easily transformed to this. You can see that this is going to happen because here we have R square and dr square. We have two derivatives in R, and we have R square. So this factor of lambda, which is a stretching or shrinking of the coordinate, is not going to affect that term. And likewise here we have a single power of R and we have a single derivative, so it's not going to affect that. But here this redefinition gets rid of lambda from the equation, and so we have this equation now in this form, which is the familiar form or the standard form for the Bessel's equation of order 0. So this equation now we can recognize as the Bessel's equation for J0 function, and we can then use that solution to represent the radial dependence of the solution. And so that is what we're going to do next.